Section 2.3, Complex Notation. We will often, although not always, use complex notation. And the reason we do that is that often things can become easier. You might think, well, hold on, complex notation is tough. Why are we using that to make things easier? Well, often it will help. Okay, we'll end up with equations that we can solve because we're using complex notation, where it'd be very difficult to do that without it. Okay. Now, we all know what a complex number is. We know j is the square root of -1. And z, in this case, is a complex number. We're plotting this on what's known as the complex plane. The circle of radius 1, okay? We've got the real axis, so any real number is going to sit on this axis. Any imaginary number is going to sit on this axis, and obviously if we're not on either axis, we've got a combination of real and imaginary. That's still an imaginary number, but obviously it's got a real component to it. Z is one such number, okay? It's a value of 1. This is a radius of 1. Value of, in terms of magnitude, of 1. And it's moved through an arc from theta equals 0, which is the positive horizontal direction, okay, through a certain angle of theta. And so we can work out what the real part and imaginary part are from basic trigonometry. That's the right angle triangle. Obviously, SOHCAHTOA, so the cosine of the angle theta will be this distance times by 1, okay? And the sine of that angle, which is that, is the imaginary part. And so we can write that in terms of trig, okay? We can write that z equals cosine of theta plus j times by sine of theta, because j, that's this bit is the imaginary part, so we multiply by j, okay? Cosine of theta plus j sine of theta equals z, which is a complex number. We can expand cosine and sine as Taylor series. So this is recalling first year maths, I think, if not before. And you can expand them as a Taylor series, and you end up with these equations. Okay, sine is theta minus theta cubed upon 3 factorial plus theta to the power of 5 divided by 5 factorial. Cosine is similar. You can define those two together. Now, we know that j squared is -1. J cubed is minus j, because we've got -1 times by j. And j to the power of 4 is -1 squared, which is 1. Okay, and so on. And so if you stick that into your equation, so cosine, we'll leave it as it is. Well, in fact, no, we'll stick j theta in there. That can accommodate for the minus, plus, and so on. Okay, because obviously here, if I mark it up, here we've got a minus sign. And obviously -1 is j squared, so we can actually join the j up with this bit, okay, and that takes account of the -1. So we've got j squared in there, which is -1, okay, so that becomes a plus. And obviously j to the power of 4 is +1, so that doesn't change that, so we could j to the 4 there. J to the 6 obviously will be minus, and so on, okay. And here, j sine theta, well, let's take the j out, okay. We've got theta minus, plus, minus, plus. So you can do the same thing again. J, obviously j times theta, and then j times theta j squared is -1 minus j. Okay, so that takes into account of that minus sign, and so on. So you end up with these two equations, and if you plug them together, you end up with this. Okay. Now it just so happens that that's the Taylor series for e to the j theta. Why is it important? So like I said, e to the j theta is cosine theta plus j sine theta. So we can use complex notation. And the reason that is that basically it's important. If you take the real part of the complex number, okay, you end up with cosine of theta. And what's cosine of theta? It's a sinusoid. And what's a sinusoid? It's an oscillation. So if you have a complex number that looks like that with the j in the exponential bit, okay, the real part of that complex number will be an oscillation. Okay, the real part of that complex number will be an oscillation. And so wherever you've seen cosine theta, you could actually use this. Okay, whenever you see an oscillation, we could often use this, or we can use cosine of theta. It doesn't really matter. And if you go back to the free oscillation case, okay, where we said x equals a cosine of omega naught t, okay, we can actually use a times e to the j times omega t, okay, omega naught t, for the same thing. The real part of that complex number will be an oscillation. That's fundamental, okay? Like I said, we'll be using that bit of knowledge throughout the course. You will come across e to the j theta all over the place. Like I said, if z rotates around the circle and you take the real part, okay, so if you go back to that circle, okay, z's going to rotate around, okay, and as z rotates around, as theta goes round, okay, if you just take the real part, that's just going to go backwards and forwards, isn't it? Okay, the real part of that is just going to increase to 1, and go back to 0, and then decrease to 1, and go back to 0, and so on. And so the real part of that complex number will be an oscillation. So why is it important? Like I said, if z rotates around that circle, and you take the real part, you return to a simple harmonic motion, okay? And if we define that angular velocity as omega t, okay, let's disregard whether there's a zero there or not. We're not talking about natural frequency, we're talking about the angular velocity. And obviously, if you multiply the velocity by time, you get a distance, okay, so omega times by t equals theta, okay, so we can replace theta, therefore, in that equation with omega t. You end up with z is cosine omega t plus j sine omega t, which is e to the j omega t, okay? And of course, you can add an amplitude and a phase angle if you wanted to. And so this bit here, okay, you've seen that before. That was a solution to our free oscillation problem, okay? And that equals, if you add the sine bit, that equals a e j omega t plus phi. And obviously, if you take the real part of this, you get this. So like I said, you can exchange the two with each other. But often it will be easier if you're using the complex notation as opposed to the trig. Trust me on that. You'll see it in a minute. So we can use this bit, this complex bit, as a trial function. So when we use cosine omega t as a trial function, we tested it out, it showed that it worked. We could actually use e to the j omega t as a trial function. And taking derivatives, this is an example of where it's easy, taking derivatives of e to the x or e to the anything is easy because it's the same thing, okay? The derivative of e to the x is e to the x. That's one of the magic things about e, okay? You take the derivative of the number, you get the same thing back, okay? And e to the j omega t, all that happens is you end up with e to the j omega t times by whatever's in front of the t. So the j omega comes out. And you do that again to get the second derivative, another j omega comes out, j squared is minus 1, so you end up with minus, and you have omega squared, because the other omega that comes out. So you end up with the same thing, okay? We could apply that to that, and you take the real part of that number, and you get x as a function of time, which is that cosine. Like I said,